Hello, today we'll be talking about quality factors and how they are calculated in CST Studio. So when we talk about quality factors, it is important to know which one we are talking about because there are a couple of quality factors that we should know, which are also called different names. So, but then basically, quality factors describe the energy losses in resonant systems. So to simply put it, it's the ratio of the effective power stored in the system to the ratio of the power lost from the system. So here you have this formula, which is Q, and then the subscript M represents the mode. So looking at this at modal eigenmodes, in terms of eigenmodes, then you have that the quality factor of associated with a particular mode is given as the energy stored in that mode. This should be subscript M here, but then and then multiplied by the frequency of that mode, then divided by the power lost from that mode to the environment or anywhere, power loss to anything. Now, so the power loss could be from the system as heat due to surface resistivity. So the surface resistivity of your system, or as radiation through the beam pipes. So you could have different ways in which your power could leave the system, and then this is split conveniently into internal losses and also external losses, where your internal losses are defined as the losses due to heat and finite surface resistivity. Now take note of this, and then the external is every other loss. So your radiation loss, your loss is through the for CST waveguide ports, so through your beam pipes, which are captured by the waveguide ports. Now, splitting this power loss into these two terms, we could define two separate quality factors. And number one is the intrinsic quality factor, which represents the internal losses in the system due to the surface resistances, and then it is an inherent property of the resistor, and then it's defined as it's also designated Q naught, which is your intrinsic quality factor, which is given as the frequency of the particular mode divided by the multiplied by the energy stored in that mode, then divided by the losses through the surface of the system. Now I've dropped the subscript M, yeah, just for convenience, but then always note that this is per mode basis. Now we also have the one thing also to mention, which we would also see, is that now for superconducting systems, we usually assume, at least in simulation and also in practical, we'll see later, but then in simulation we assume that Q naught is infinity. So which is that we have zero loss here, which you would also see that, okay, if we have zero internal loss because the surface resistance is zero, then we have that the internal loss is P in tends to zero as the surface resistance tends to zero, and then your intrinsic quality factor tends to infinity. Although in practice this is not the case, but then the value is large enough that we'll see some simplifications. Now the external quality factor, all other captures the losses due to all other mechanisms. So it accounts for the energy loss due to coupling with external components, waveguides, probes, or any other thing. Now, and this is also defined as the energy stored divided by the external power loss. Now, the loaded quality factor, which is what we have from this definition, is defined as, remember we started with this definition of P loss under here, but then we split P loss into P internal and P external. So we could do some mathematics, and then we have that yes, so if we should invert this, then we have that the inverse of Q loaded, as we define it now, is the internal external power, and then we could split that. Then we have this nice relation that the inverse of the Q, the loaded quality factor, is equal to the inverse of the external of the intrinsic quality factor plus the inverse of the external quality factor. Now, what can we say from this? So we see that for superconductivities, as I just mentioned, the intrinsic quality factor tends to infinity. So if this tends to infinity, this particular term here would tend to zero, which means that your loaded quality factor is approximately equal to your external quality factor. Now note, This is for superconducting cavities. Now, the intrinsic quality factor, I mean, even for real cavities, it's usually high. I think from 1e to maybe from 1e to 9 to 1e to 11. I think around this value. So even though in real cases, in real life, you have that this is finite, but then you still see that the ratio, when you divide this, the contribution to the loaded quality factor is negligible, and the external quality factor dominates. Now this is for superconducting cavities. Now for normal conducting cavities where you have high resistivity, I mean relatively high resistivity, for example, you use copper, then this plays may play a more important role than your external quality factor depending on your setup. So if this actually dominates, which means that your external quality factor tends to 0. So for example, you have maybe a system where you do not have power leaving the system, or the power leaving the system, it's very small. Then you have that your external quality factor tends to infinity. So for example, trap modes in a cavity. So trap modes in a cavity, you have that the energy do not propagate into the external port. So what you would expect, at least in a bare cavity, so that's without couplers, okay, because then when you put couplers, then you still have some energy going through the couplers, but it still depends on which mode we are talking about. So for some modes where you have the energy concentrated in the cavity and very little propagating into the beam pipes, then for an infinitely long beam pipe, you have that the external quality factor would be infinite, which would mean that your the loaded quality factor becomes approximately equal to your intrinsic quality factor. Now, for normal conducting case, again, depending on the setup that you have and the modes you're considering, you might have that the external quality factor tends to infinity, which would make this term 0, which would make the loaded quality factor equal to the intrinsic quality factor. But in a case where you have an interplay of these, so you have losses going through the walls of the cavity, and it's not that much greater than the losses, so it's kind of a balance, let's say 50-50 or 60-40, then you have to consider these two terms in the calculation of the loaded quality factor. So the intrinsic quality factor in is calculated in CST using the perturbation method, and then for this you would have to specify conductivity. We would see that, and then the external quality factor can be calculated using different methods, which can be found in literature. So there are different methods to estimate the external quality factor, and we are going to look at those now. This one is pretty straightforward. So I mean, straightforward in the sense that, yeah, there's really no confusion about it, at least in CST Studio. But then the external quality factor over the years, there have been some, at least for me, some confusion about it, because as I'll show you, you have from the different versions of CST Studio, and you have the different definitions of external quality factors. So one of the methods that you could calculate the external quality factor is the power flow through the port. So you estimate the power flow through each port that you have in the system, and then sum everything up, which would give you the total power leaving from all the ports, and then you find this ratio. This would give you external quality factor. Now in CST 2022, I have 2022 installed here. I have 2020, but I haven't checked. But then in 2022, you have some external quality factor. Should I toggle to that? Okay, maybe when I'm discussing it, then I'll come back to this. You have some external quality factor, which I checked in documentation, and it seems that this is what they were doing. So calculated the power from the port and then found this ratio. I mean, just also note that the energy in CST is normalized to 1, so this would just be omega divided by p port. Definition of the terms, then the complex eigenfrequency method, which is the one I usually use, and this was, now I can't remember when it was introduced, but I think from 2020 it was already there, but then under a different name. So this this method can be used when you select lossy eigenmode solver in CST Studio, and Yeah, this is because the frequency, so basically the external quality factor is calculated from the ratio of the real part of the frequency to 2 times the imaginary part of the frequency. And this is because for your lossy eigenmode solver, the frequencies you have that are calculated, they are complex and no longer real. So you have the complex part encoding the losses in the system. So that's where this you have this formula from. For now, I don't. Okay, yeah, have I? No, I can't recall looking at the math that resulted in this, but then for now it's not very important though. Yeah, for now it's not very important. So these are some methods. In the literature, there are some other methods where you use some lossy material and place it at the end of the beam pipe and then calculate the energy loss to that lossy material. So basically, you're looking at something like this. So instead of using port modes in CST Studio, you define a lossy material that is non-reflective. So you have to optimize it to be non-reflective so that you don't have energy getting back into the system. And you calculate the power dissipated in that or lost to that lossy material, and then you find this ratio. So that's kind of a not so brief rundown of it. And then now we have a look at do I need to do this? Yeah, okay. Oh no. So I went ahead and for in CST Studio you have these different solvers. So you have automatic, you have classical, which is the lossless, and also general, which is the lossy. Now this is CST version 2023. Now if you should go to 2022, then what you're having for the eigenmode solver is you have the default and the lossy. So the general lossy eigenmode solver. Now the default in this case is the lossless. Now if you should go to 2020, which I haven't checked. I hope it opens on time. I do not know if I can open any project. Okay, yeah, just a test project, and then now why that loads, I also checked 2025. 2025 is consistent with 2023 version. So what you have in 2025 is lossless, classical lossless, and also lossy. Now in 2022, what you have is for the eigenmode solver, what you have is default and preview. Now default is the lossless and preview is the lossy. So that's it. I don't think I have any other versions. Let's see, CST 2019. I think I should have. Okay, I don't have 2019. I don't have it installed. Probably my old system. So just so you know, it has the name has changed over the years, but that's what they correspond to. I haven't checked 2024. I have refused to upgrade to 2024 and also to 2025 because then I have some backward compatibility issues and have to run all of my simulations again, I think, or at least that's what it asks. So stuck for now with 2023, and there you have automatic, so it automatically selects between classical and general, so the lossless and the lossy. So what I went ahead and did was to okay, maybe I discuss the lossless first. So for the lossless case, you see we do not have any ports defined, but then there's also one with ports. But then for the lossless case, I think what happens is that if you should define a waveguide boundary condition, it's not really considered. I think this is what happens, and the reason why I say this is because it does not yeah, I'm sorry about that. So what was I? It's so for the lossless, now I've lost my train of thought. What was I saying? So for the lossless case, it does not calculate the external quality factor. So if you should look at the Q factor, lossy. Okay, I think I'm getting ahead of myself here. Let's get into the different quality factors that could be calculated using CST. Then we get back to the result. So if you should go to the result template, and also this is different depending on the version you're using, and then you go to 3D eigenmode result and check. Now on the list you could see Q factor perturbation. Now what this calculates, if you should select this, what you have is that you could change the material conductivity, because the default material conductivity here is that of copper, which is 5.8 e to 7, but then you could change the material conductivity. So what this calculates, it's the intrinsic quality factor. So using perturbation method, I'm guessing that's, or I think, if I remember correctly, that what is perturbed might be the permittivity of the, I can't remember if it's permittivity and permeability or just permittivity of the system. And then not to get too much into the details of the perturbation method, I mean that CST uses, but the general idea is you perturb the system and then calculate the shift in frequency and then use it to calculate the intrinsic quality factor. So what it calculates is the intrinsic quality factor. Now this is for 2023. If we should go to 2022, then you have what is it called? I think what I'll do is I'll compare this drop-down menu. So you also have Q factor perturbation. Then on this list, so this is 2023. What you also have is that you see Q factor lossy eigenmode. So for lossy eigenmode, it's calculating the external quality factor using the real part and the imaginary part of the complex frequency, which arise from the lossy eigen value problem. Then for 2022, what you have is you have Q factor lossy eigenmode. Then you also have Q factor external. So Q factor external, I looked into the documentation and it seems that this is how they calculate it. So Q external divided by the power flow through the port. But yeah, I can't remember if there was information about how they got this power, if they integrated the field at the plane of the port and then we're able to calculate this power flow through the port or something. I can't remember if it was mentioned. So this is 2022. So you have the Q external, which is calculated using the power flow through the ports. And then you have the loaded quality factor, which is a combination of your Q factor perturbation, which is your intrinsic quality factor, and the lossy eigenmode or the Q factor external. So these two ideally should give the same result or similar result. So now I'm thinking of it. Probably I should run a simulation to compare these two. Maybe I'll do it because I've been on 2023. I usually work on 2023 nowadays, and then you don't have this option in 2023 that you don't have these options for the two methods. So you just have the lossy eigenmode method. That's the only one you have available here. So you only have two quality Q factor calculations, which is the intrinsic and the external quality factor. But in 2022, you have the intrinsic, and then you have some other ways to calculate the external, and then you have the loaded, which is a combination of the two of them. Let me see what they have in, no, not this. Let me see what they have in 2020. So in 2020, you have Q factor perturbation, then you have lossy eigenmode, external and loaded. Okay, so it's the same thing as 2022. Now for the perturbation, so Q factor perturbation, you could also calculate it in post-processing from here. So losses, loss and Q, and then look at the conductivity. You could specify different conductivity here, and then you calculate it. So I think if I should change this, then you can calculate the intrinsic quality factor with the perturbation method. So which one should I go back to? Yeah, this. So what I did was, for the lossless case, I went ahead and calculated the external quality factor, which of course you cannot get because it does not calculate it. So for this case, there are no ports inside. So the boundary condition I used is magnetic boundary condition, because also in the lossless does not support open boundary conditions. And I think even with open boundary conditions, I don't know, probably there would have been some way to calculate that, okay, this is specified as open boundary condition, so check the power flow through this plane, and then with that you can now get the quality factor. I think that yeah, could also be possible. I think that's also one method you could use to calculate it. Then so for this you have just zero, just return zero as the external quality factor. Now if you should check even including ports, so I also ran the simulation just in case for lossless, including waveguide ports, and then let me see what my boundary conditions are. Yes, also magnetic. I don't think it considers the waveguide port boundary conditions. I don't think it considers it, because then you have that the external quality factor from this is still, it still returns 0, even though this is classical lossless, and even though I selected to consider ports in the simulation. What else? Then for the lossy, of course, if I should run the lossy without ports, then of course it doesn't have anything to record, so the Q factor is also 0 return. That is, the lossy eigenmode acts as your lossless without, if you do not have any ports defined. And I think now you should, yeah, there are so many iterations to check, but I haven't checked this. Now, so this is your lossy eigenmode simulations without ports, so it acts as your lossless and returns real eigen values. So you have that your Q factor is 0. And then for the lossy with ports, then you have some values for the Q factor external, so the external quality factor, because it calculates the power flow through the ports. There's something I wanted to mention now that I think I forgot. Okay, now you could also check. Oh, I didn't even consider ports. I didn't even consider ports. Now I wonder how the results would change if I should select consider ports, because I thought I selected this, or probably it automatically selects it. Okay. Oh. I think what I'll do, maybe I'll select a port and then compare, but I don't think it would be different. I don't think the results would be different. And then one other thing that I could check, or you could check, is consider this is consider material losses in post-processing only. That's, you should postpone the Q factor calculation to post-processing. Okay, so this acts as it should, but then even without selecting constraint ports, so probably something intrinsic in the general lossy eigen value calculation. So how do the results compare? So first of all, we've seen that you can calculate your external quality factor using your lossless, which is your classical eigenmode solver, because then you have real eigen values. But then with the other methods that I mentioned, that you could possibly specify maybe a lossy material at the end of the beam pipe, so at the end of the beam pipes, and calculate the power there, then probably you could calculate perhaps you could calculate the power, the quality factor, even with your classical lossless eigen value solver. Yeah, I think it should be possible. So I compared the results from all of the simulations, and then first of all, if you should look at the frequency, then for the lossless and the lossy, so without any port, you see that the values are exactly the same. So what I mentioned, that the lossy acts like lossless in the absence of waveguide ports. So this is what you have, and then the lossy calculated some extra modes here. Now if you look at the lossless and the lossy with ports, then you see that it's almost the same, but then you have some difference here now, probably maybe mesh resolution or something, but then you do not have the exact match. But I think it's numeric, not depending on the system. And then when you compare both of them, so with ports and also without ports, then you see some discrepancies. But then I tried going through each and every one of the modes to see why the discrepancy is there, and what I observed was that for these modes you had a stronger field in the system for the lossless, for the systems without ports, and the systems than for the systems with ports. And these were, let me see, I think they were waveguide, or no, not waveguide modes, coupler modes. Let's see mode 3. So mode 3 is let's see, mode 3 is a coupler mode. Yeah, it's a coupler mode. And then if you should look at for the case with ports, then you have this coupler mode also. Yeah, it's a coupler mode, but then you see that the, okay, what's the scaling? I think I just reset scaling. Yeah, so you see it's the same mode, but then I think what happens is that because there's a port and the mode is free to propagate, then you have some shift in the real part of the which is the frequency. In the real part of the frequency, this is what, or a large shift in the real part of the frequency, this is what I think might be the case with these modes. If you know maybe some other explanation, or you think it's due to some other thing, maybe leave it in the comment. Because yeah, I checked for the other modes that you have like these big discrepancies in the frequencies, and then they were, look at port 6, it was majorly, yeah, it was your coupler modes. So this is the reason I could come up with on why you have this shift in frequency in the real part of the frequency. So, but then aside that, every other thing lines up. And then for the lossless case, even with ports, you can't calculate your external quality factor, except maybe you come up with some other method. But then for the lossy case, you can calculate your external quality factor. Then you also have your perturbation. One thing I also did was calculate the Q factor perturbation, which is the intrinsic quality factor, and then you have this yeah, plot, and then you see that for the what's it called, for the coupler modes I showed just now, which was mode 3, and mode 6, you have that these are where you have your, or was it mode 5? No, I think it was mode 6. So what is going on at mode 5? Let's see, because you have that it's pretty much remains pretty much aligns in some modes, and then some other modes it doesn't align so much. So let's look at mode 5, what is going on there. I think mode 5 is a proper cavity mode. Yeah, it's a proper cavity mode. So but then the intrinsic quality factor is calculated differently. What could be the reason for this? Let's see. So, and then it's like a huge difference. Okay, I wouldn't spend the time now to think of why this could be. If you know, please leave it in the comment yeah, section on why you have this. But then for the other modes, you have pretty much that it aligns, and I think these modes are the modes that are strongly, these modes are the modes that do not propagate into the cavity, and then these ones are damped. I think that may be it. For the damped modes, you have, so let's look at, I mean, just to check it quickly, let's see mode 8 and mode 9. From my hypothesis, this should be concentrated. Yeah. Okay, they are not strongly damped, but then I'm seeing the maximum field. It's somewhere here. That doesn't look right. But yeah, I would expect the external quality factor of this mode to be, yeah, somewhat high. So let's see mode 8. Oh, of course I can't calculate it from this. Mode 8. I mean 11 is higher, so let's see mode 11. 6. Many part of it going through the beam pipe. Yeah, some part is going through the beam pipe, but yeah, if you know the reason why you have this, maybe just leave it in the comment section. I would also have a look at it and see why I have this, why there's this difference in these modes. Can't think of anything from top of my head now. Yeah, so that was it, just showing the different quality factors that, and also what they mean. Now, one last thing is in the calculation of the external quality factor, in the specification of the port modes, for your TEM line, which is your transverse electric magnetic lines, since you don't have any cutoff basically for your TEM line, so for the couplers and then for the fundamental power coupler kind of tiny model, you just specify one mode. So I'll show the port definitions for these. So this is just one mode for the TEM line, and port 3 also is just one mode. It's just one mode. But then for the beam pipe, depending on the frequency range you are considering, you should consider increasing the number of modes to capture the power, because if you do not consider enough amount of modes, so for example, let's say you only consider two port modes, then the first two port modes would be T11 and T11, and then you wouldn't have any component of your TM010 mode. So the values you'd calculate for your fundamental mode for the Q external would most likely be very, 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 very wrong. So yeah, just something to point out. I think I'll do a video sometime later, explaining this in detail, but I think for this video this should be enough. Just wanted to mention that so that if you try running the simulation, so you know the number of if you should try running this test yourself, so you know the number of port modes I considered. And the reason is because I was only considering the first monopole and dipole passband, so it's not really a high frequency region. So the fundamental mode of this cavity should be around 400, should be 400.79 megahertz. So I just considered 390 to 600 megahertz. So I think that's it for this video. If you have any questions, leave it in the comment section below. If there's anything that I said wrong, also please point it out in the comment section below so that others can learn, and probably it was a mistake, or probably I just did not know, so I could also learn too. So yeah, so many combinations of this, but then I showed just this for, but then you could try out different things. For example, checking this, I don't think this should change the result, but yeah, I wouldn't want to run it now. And then the other thing I said I was going to check, now I've forgotten. Yes, if you have CST 2020, maybe you could check the Q factor lossy eigenmode and compare with the values with the Q factor external, and maybe also let me know in the comment section if they're the same, or if there was some difference. And then yeah, maybe I could also see and then maybe check into why it was different, and maybe look really into how this was or is calculated, at least in the 2020 version. So how this one is calculated. So yeah, that was it for this video. Thank you for watching. I hope you learned something and yeah, till next video. Ciao.